Hello, astronomy. Welcome to our second video in Unit 6, and what will likely be our last video both in Unit 6 and our last virtual video of the year. It's almost sad a little. So the last thing that we talked about in Unit 6 was the idea of how we determine how far things are away in space. We talked about Cepheid variable stars and type 2 supernova and parallax and things like that. The second half of this unit goes into a bit of relativity, and we're going to end sort of with the Big Bang. So we've already discussed briefly how one of the pillars of Einstein's theory of general relativity was the idea of what he called space-time. Actually, I'm not sure he used the term space-time, but we use the term space-time. And this idea that space and time is sort of like a fabric, and that it can dip inward, it can curve. And objects that have gravity bend the fabric of space, what again is called space-time. The yellow circle has more mass, the brown middle, the red the least. And you can see they're bending space-time. The amount is based upon how much mass they have. Now, obviously, this creates gravity, something that falls into the sort of well of the yellow marble. Say this is Jupiter, would fall into Jupiter. But it also affects the light. Light will bend around space-time like a marble kind of bending around the curvature of the gravity well. So this is true. Light actually does slow down when gravity gets stronger. If we've been able to watch the movie Interstellar in class, which is a great movie, it talks about there's a scene or a segment where they're on a planet orbiting a black hole, and time for them is something like every minute they're on the planet, 7 years pass on Earth, because for them time is slowed down because they're so close to a black hole, whereas on Earth it's relatively faster. So time can bend around the curvature inside space-time. So one sort of, if we have a clock on Earth versus a clock in orbit, the clock on Earth is closer to Earth's center. It actually does go like a nanosecond, I don't know the actual number, but it goes a very, very small but measurable amount slower if it's on Earth than if it's in orbit. So, this has actually been proven that light or mass actually affects the curvature or the path that light takes. So in this diagram, so let's say that I have some stars and I have the sun and you're here on Earth. Obviously you would be, if you were at this telescope, it would be daytime to you because you're facing the sun, so you actually wouldn't see the stars at all, unless it was a solar eclipse. So if I have a star that's right here, okay, the way that your eye works, when your eye sees things, light, or your eyeball assumes that light travels in a straight line. So if I'm looking at my computer screen, it's because light's coming from the lights in this room, it's hitting the computer screen, light's being reflected in all directions, but some of that light's hitting the screen is coming back to my eyeball. And I see the screen in front of me because my eye assumes that light traveled in a straight line. Okay, that's how your eye and your brain works. So if I have a star that's right here, actually a star that's here, the actual position, a ray of light that came out from the star toward the sun would be blocked by the sun, right? A ray of light that came out at an angle past the sun would follow kind of like this path, and it wouldn't come to the telescope. But because the sun has such strong gravity and the sun bends light, the star's light comes by the sun and then curves a little bit toward the sun and hits my telescope. So the actual position is behind the sun, all right? But because the light bends around the sun, my eyeball thinks that the star is actually, in this case, to the right of the sun. That's not where it actually is, but it's where my eye thinks that it is. It's like the idea of you put a pencil in a beaker of water and the pencil has the light's refracted and the pencil looks broken. Refraction just means the light got bent. Well, in this case, it's the sun's gravity bending light. Now, light doesn't really have mass, right? So how does gravity affect things that don't have mass? Well, that goes back to this. Like, this is Einstein's theory of relativity with space-time. A star further away from the sun, like notice the further away you get, see the distance between the apparent and the actual position here. Here it's getting smaller because you're further away. Here, you can't even tell that there was a difference because it's negligible. Now, all this happens during the daytime. So how, for you to observe this, the light has to have passed the sun, which means it's daytime. So how in the heck do you observe this? And this is one of the things Einstein theorized. Well, the only way to do it or the way that it was discovered, was to do it during a solar eclipse. So look at this diagram. Say that I have the stars here, the light bent around the sun. The star is actually here, but it appears here. How could you tell the difference? Well, during the daytime, you can't unless you have an eclipse. So in the year 1919, this was shortly after Einstein theorized this, there was going to be a solar eclipse. I forget where it was visible, but it was a big deal because men of science, I'm sure there were some women there too, men and women of science more or less agog over results of eclipse observations, lights all askew in the heavens. Einstein's theory triumphs. Stars were not where they seemed or were calculated to be, but nobody need worry. Basically what they did is they, a star, you know where the stars are supposed to be, even during the daytime, you know where the star is at night, you know how fast the stars move through the sky, you know where they're supposed to be during the day. So basically the idea here is where this star is supposed to be during the day, because again, when you see the star at night, the light's not big because it didn't go by the sun. So you know it's supposed to be here, but you actually see it here. If it's supposed to be blocked by the sun, but it's not blocked by the sun, it's because the light got bent. So a solar eclipse basically helped prove Einstein's theory of relativity, his idea of space-time. This is a picture from the 1919 solar eclipse. I'm not sure anything is useful from this picture besides it's just an actual photographic plate from the eclipse. But if you saw a star here that's supposed to be here, that's basically how they prove relativity. So gravitational lensing is another sort of effect of the idea that mass can bend light. So, you see a picture, look at this image. You see a very bright star. I assume it's a star in the center. Then you see this ring around it. Like, what the heck is that? Well, the ring, it looks kind of like a lens, right? Well, the ring is actually one object that's behind the star. So the way gravitational lensing works, so here's the Earth, here's my telescope or my probe, say it's a satellite. Here I have a big galaxy with lots of gravity. Here I have an object. I think this is showing maybe a pulsar or a quasar. Something, actually this could be a black hole too. Something on the other side, actually it wouldn't be a black hole, we shouldn't be able to see it, but something on the other side of the galaxy. So, this object gives off light going that way. I can't see that. Going that way, I can see that. Well, light that came, light going toward the Earth would be blocked by this galaxy. So really, you shouldn't be able to see it because it's behind it. Well, light that was given off this way got bent toward the Earth, and suddenly I see it. Light that came off from the bottom, or in this case, the right side of whatever this is, got bent toward the Earth, and I see it there. And picture these arcs also going up and going down around the galaxy. And basically, if the objects are perfectly aligned, you get what looks like a ring from that object. Gravitational lensing, this is another diagram showing it. So here's me, this green circle. Here's the object. Massive gravity field, maybe it's a galaxy or whatever. The light gets bent around it to where I see it as a ring. This is another one. So this might be one where the objects are not perfectly in line. Maybe it only gets bent above and below. Maybe the object's a little bit below the plane of the three objects. But basically, these two red things are actually the same thing that's located behind say this is a galaxy. This has been discovered with quasars. We haven't really discussed quasars. Quasars are very strong radio signals, and they're some of the most distant objects in space. We're actually not quite sure what they are. But yeah, gravitational lensing, and these are also nicknamed Einstein rings for a reason. Here you see a bunch of different ones. Basically, it's an object that's behind the object in the center, but the light's being light's being bent around it due to gravity, okay? Okay, so the deal with the solar eclipse and the deal with gravitational lensing helps prove that light can be bent by space-time. So I want to do a quick throwback to Wien's law, or Wien's law. So remember we talked about this back in unit 3. The peak wavelength that an object emits is based upon its temperature. And if your temperature is 5,500 Kelvin, which is pretty hot, you peak in green. If it's 5,000 Kelvin, you peak in yellow. You get the idea. That what determines an object's maximum wavelength that's it's emitted, not reflected, that it emits, like a light bulb, is based upon its temperature. So people have known about this for over 100 years. This isn't a new thing. Well, let's just say that what would the peak look like for human body temperature, or the temp of your skin, all right? Say 70 degrees Fahrenheit room temperature. So that peak, so these are peaking in visible light, right? That peak, notice how the peaks are going a little bit to the right every time. If I made this, you know, in my head, I'm suddenly can't convert Kelvin to Fahrenheit. Say I did it to 70 degrees Fahrenheit, the peak would be way over here, and it would be very, very small. The numbers for the wavelengths would be, I mean, the longest would be radio waves, maybe it peaks in microwaves, but it's going to be a peak very, very small. So actually, before we do this, let's talk a minute about the Big Bang Theory. So the Big Bang Theory, I'll go back to that previous slide in a minute, was proposed by a Belgian priest named George Lemaitre. It was theorized by a Catholic priest, which, you know, it's one of the things people hold up. Science and religion can actually get along. He didn't call it the Big Bang. He called it, he used the term a day without a yesterday. Kind of cool. So he knew about the universe expanding and all of this. And he basically theorizes, well, if you wind that backwards, play the movie backwards, you're going to wind up where all the matter and all the space of existence was in one single point. And at that point, you know, before that point, it was a day without a yesterday. The name Big Bang came from a British scientist named Fred Howell. He was a very, very famous, a very preeminent physicist at the time, had many good discoveries on his own. But he sort of was disparaging the idea in a radio broadcast and called it the Big Bang, like, ooh, it's a Big Bang. And the name stuck. So the irony is the guy who named it, and he never really accepted the Big Bang, he never really advocated for it. Even when it became more and more accepted, he still wasn't a fan. So the guy that named the Big Bang, you know, wasn't the guy who proposed it or even accepted it. So this guy, George Kemal, who we're going to discuss, so this is Lemaitre, this is George Kemal. He was Russian. So he sort of takes this idea and says, so let's say we have the Big Bang, right? So one thing about the Big Bang that we have not discussed yet is for about the first 380,000 years, give or take, after the Big Bang, the universe is very hot and it's very, very dense. And it's so dense that if like a light bulb was turned on and it gave off light, there'd be something so close to it that absorbed the light could never like freely travel through existence. It would always be absorbed by some nearby object. I can see my computer screen because light's going from my computer to my eyeball, nothing is in between. After about 380,000 years, before that time, the universe is said to be opaque. You know, we observe things that we see, either visible light, infrared, whatever. If there's no radiation from it that escaped, we can't see it, right? After about 380,000 years, the universe has expanded and is kind of cooled down and shut out enough to where light or energy from that period is still going through space. And if the universe is expanding, if we have, you know, sort of the cosmic redshift, which we do, that energy is still going through space. It would be bathing the entire sky. We would be part of it, right? And it would be redshifted. So Kemal theorized that there should be, I think he said between 5 and 10 Kelvin. Here you see it's 2.7 Kelvin. There should be some kind of background radiation from the Big Bang from that moment, say 400,000 years after the Big Bang, that's been redshifted. And he used Bean's law and whatever math he used to predict what wavelength it would be at. And he predicted that it would be at, and it would have redshifted into the microwave part of the spectrum. Now, Kemal couldn't, microwave or radio telescopes weren't developed enough at the time to detect the radiation. It wasn't until later that it was actually detected. But of note, I'm just going to read this slide to you. The entire universe emits a thermal spectrum of 2.7 Kelvin, which corresponds to a peak wavelength in the microwave area of the EM spectrum. This is referred to as cosmic microwave background radiation. The discovery of this is a fascinating story because, you know, Kemal theorizes it and no one can detect it because the telescopes aren't good enough yet. And it's not really a widely known idea. And then later when the telescopes got better, people were actually looking for it. Now, the two guys that actually found it, Penzias and Wilson, were two scientists working at the Bell Telephone Laboratory. Is in New Jersey. It's still there. You can visit it. And they were working with this sort of horn-shaped microwave telescope, and they were using it. The Bell laboratories, that was for like telephones and stuff. They were using it to try and communicate with satellites. They were in no way looking for background radiation. They were just building a telescope to use for practical purposes. And they kept, they were, one thing when you have a new instrument is you want to, like any background noise, you want to cut out. So like if you're on a telephone and there's background static, you want to filter that out because you don't want that. But they kept finding, this is in the 60s, this background noise around 2.7 Kelvin, and it was everywhere in the sky, and they couldn't get rid of it. And the part of the funny story is they thought that it might have been that there were pigeons, like the pigeons nesting in the antenna, and they had pooped, and they climbed in it to clean out the poop, thinking maybe the bird poop was what was causing the interference, and it wasn't. It was still there. And then later, they realized what they had discovered was basically, the echo remnant of the Big Bang, and they published it, and they got the Nobel Prize for discovering cosmic microwave background radiation. These two gentlemen here, and this is an NPR story. Now this is NPR, so there's no like video. It's just sound. This was actually put out in 2005. 2005 was the 40th anniversary. So now we're over 50 years. And this is 7 minutes. I'm gonna play it because it's just cool, where they interview the guys for the anniversary, and they kind of tell the story. So let's just listen to this. I'll scroll through because there are some pictures.
NPR News, this is All Things Considered. I'm Michelle Norris.
And I'm Melissa Block. A clue about the origin of the universe was discovered 40 years ago. In 1965, the world learned that two astronomers had stumbled onto something that seemed to prove creation occurred all at once long ago. On May 21st of that year, a headline on the front page of the New York Times read, "Signals imply a Big Bang universe."
The discovery was an accident. Arno Penzias and Robert Wilson were only trying to clear unwanted noise from a radio telescope. They later won a Nobel Prize for their work. Scientists have labeled the discovery the greatest scientific discovery of the 20th century. Here's commentator Ralph Schoenstein.
Listen now to the oldest sound you will ever hear. That's the echo of a baby's cry. The newborn universe announcing its arrival 13 or 14 billion years ago. The heat of the Big Bang, the greatest heat ever known, created radiation that spread throughout the expanding cosmos. It cooled, and it still lingers. If you are feeling self-important today, you may feel less so hearing this never-ending primal sound. Let's climb the small hill to where these two men, the New Yorker Penzias and the Texan Wilson, had a backward look more dramatic than that of Lot's wife. We're at the Bell Labs in Crawford Hill in northeastern New Jersey. From up here, you can't see to the end of the universe, just to the end of Asbury Park. There is a turntable with a gray horn antenna, and with it, you can hear a dawn that came up with considerably more thunder than the one on the road to Mandalay. Robert Wilson, who lives nearby, came back here for the 1,000th time to take me into the little shed attached to this horn antenna. Inside, there's something that looks like a tabletop gyroscope.
Oh, the gears are really stuck now, but this would turn this way and be driven by a clock at the same rate the Earth rotates.
It's a computer that cost $25,000 in the early 1960s and keeps the big radio telescope pointing at the stars.
But any PC would have no trouble doing this job. In fact, my Palm Pilot would easily do this job.
In other words, a teenager today could tune to the Big Bang in a Burger King. This horn antenna, which looks like a giant ear trumpet, was never used for its original purpose, to trace signals bounced off a satellite. So Bell Labs let Penzias and Wilson use it for other things. In another shed are boxes of fiber optic cable. Squeezing into a corner, Wilson tries to turn on a system that moved the great antenna on its turntable.
Now I'm going to try turning it on. You'll hear a loud noise. It takes about a minute to warm up.
The system is still in good shape, and so is Robert Wilson. When he and Arno Penzias first came here, he had just left graduate school. They had some projects for the radio telescope, but first they wanted to make sure it was making contact with the Milky Way and not Jersey City. They needed quiet. Instead, they found noise.
We call it noise because it's completely unstructured. It's random signals.
It was a strange, maddening hum.
We tried hard to think of where things came from. We believed in physics. It had to come from somewhere.
For a year, they checked to see if the military was testing anything. It was not. And then, inside the horn of the big antenna, they found the droppings of pigeons.
It just happened that this thing was stored in a way that the pigeons could use for their nesting place.
But it was cosmology, not ornithology, for these two men, so the pigeons had to go.
We captured the pigeons initially, and then we sent them to Whippany, which is another location some 30 miles away, and the pigeons came right back.
Arno Penzias. He now lives in San Francisco, and he remembers those misplaced birds.
We then thought of trying to have ways of discouraging the pigeons from staying there. We weren't able to do that. We finally, and I'm not happy about this either, but to get rid of them, we finally found the most humane thing was to get a shotgun, and got a shotgun, and at very close range just killed them instantly. So it's not something I'm happy about, but that seemed like the right thing. It seemed like the only way out of our dilemma.
And so the pigeons left with a smaller bang, but the noise remained, coming from every direction. Penzias thought of Sherlock Holmes.
When you have excluded all the impossible explanations, the remaining explanation, however improbable, must be the right one.
The great search might have ended right there, but Penzias learned that across the great void of New Jersey, at Princeton University, Professor Robert Dicke had been predicting that the residue of the Big Bang would be low-level background radiation throughout the universe. Penzias called him and learned that Dicke and physicist Dave Wilkinson were about to build a device to hunt for cosmic background radiation. However, Princeton was going only for the silver. The gold was at Crawford Hill.
Dave Wilkinson tells the story that when Arno called, he and the other people were in Dickey's office having a bag lunch. And Dicke picked up the phone when it rang and talked, and they heard words like antenna temperature and atmospheric brightness. And Dicke put down the phone and said, "Well, boys, we've been scooped."
Remarkably, the Princeton and Crawford Hill teams had done theory and proof within 40 miles of each other, the best New Jersey collaboration since Thomas A. Edison asked himself what a filament in a vacuum tube might do. Although the teams both published papers, it was Penzias and Wilson who, in 1978, won the Nobel Prize for what has been called the most important scientific find of the 20th century. Two non-Ivy League astronomers who had gotten curious and unlocked the secret of how the universe had come to be. They had canceled out the competing theory, called steady state, that said there was no moment of genesis and will be no apocalyptic end. For Penzias and Wilson, it will be apocalypse sometime. Because of the anti-evolution movement, some American schools now are also questioning the Big Bang. But two men who heard a strange noise in northeastern New Jersey 4 decades ago would say to these schools, "Do your homework." For NPR News, this is Ralph Schoenstein.
Photos of Arno Penzias and Robert Wilson and the horn antenna are at npr.org.
Okay, cool. So that's a pretty good background to the story. Just a couple updates. So NASA had a mission in the 80s and 90s called the COBE mission, where they launched a satellite that basically bathed or tried to search for this background radiation bathing the entire sky. This is what they found from this radiation, the Fluorine law curve. Notice where it peaks. It's peaking at a temperature of 2.74 Kelvin, which is what the other guys found. And the wavelength is in the microwave part of the spectrum. So basically, this is the most accurate. Look how perfect each point and where the peak is fit the predicted curve from Wien's law. It's beautiful. So I want to just read this to you real quick. So this is something I got from space.com. So for the first 380,000 years or so, the universe was essentially too hot for light to shine, according to France's National Center of Space Research. The heat of creation smashed atoms together with enough force to break them up into a dense plasma, and opaque soup of protons, neutrons, and electrons scattered light like fog. Roughly 380,000 years after the Big Bang, matter cooled enough for atoms to form during the era of recombination, resulting in a transparent electrically neutral gas, according to NASA. This set loose the initial flash of light created during the Big Bang, which is detectable today as cosmic microwave background radiation. However, after this point, the universe was plunged into darkness since no stars or any other bright object had formed yet. It says after that point, it basically means before that point, going back to the Big Bang. About 400 million years after the Big Bang, the universe began to emerge from the cosmic dark ages during the epoch of reionization. During this time, which lasted more than a half billion years, clumps of gas collapsed enough to form the first stars and galaxies, whose energetic ultraviolet light ionized and destroyed most of the neutral hydrogen. So this is the idea of, this takes us to where we are, not today, but where we began with the formation of the solar system from clouds of gas and dust called nebula. This is sort of a graphic of it. Notice before about 380,000 years, you don't see anything. So, we can't actually, if you found a signal that was 13.8 billion light years away, would that be the Big Bang? Well, no, because that first about half million years, light doesn't penetrate. So we can't actually probe to the point of the Big Bang. We can only probe to really the background microwave radiation. And after this point, you start getting the formation of galaxies and stars and so on. The furthest thing the Hubble has found, and this might have been scooped since the last time that I looked it up, but 11.1 billion light years away is the furthest the Hubble has seen. The Big Bang is 13.8, right? So you'd have to get 3, 4, 5 billion light years further away to actually see the Big Bang. But again, you wouldn't because of the opaque nature of existence after the Big Bang. And this is just another little diagram that shows times and such. The last thing that I want to leave you with, and I alluded to this earlier in a different video. So, we discussed how the universe is expanding. Well, the universe is expanding in some places faster than the speed of light. So how can that be? Things can't go faster than the speed of light. So it's not that, if creation were an actual explosion, like you have a center and you have an explosion and you have an end of the explosion. The explosions, that cloud could be getting bigger, but you have a middle and you have fringes. That's not what we observe. There is no middle. Basically, you observe the universe, the same type thing, no matter where you are. You can't be closer to the middle or closer to the end. And this leads to the idea that space itself is expanding, which that can happen faster than light. All right. Basically, between galaxies, new space is being created, which is, it's like two things embedded in flypaper, and the flypaper is getting bigger. So you're still seeing the redshift. It's called a cosmological redshift because the objects aren't actually moving away from one another. Space is increasing. So what's the Big Bang like? One explosion? No, it was just the point in time and space when everything began to be. And before that, there was nothing, at least that we know of. Is the space between Earth and the sun expanding? No, because gravity would overcome that, right? Gravity is what keeps the sun and the Earth locked in their current positions. But between galaxies where the gravity is negligible, space itself is actually expanding. Okay, so that's a good place to end. All right, thanks.